Okay, welcome to part 2 of the tutorial on making end caps yourself for your own self-build DIY modules, WTCs, whatever you like to call them. I've got a couple of cylinders here. They're only basic examples. They've got no equipment or any sort of guts inside them. That's deliberate. I don't want to complicate things by showing all that sort of thing. The main thing we want to concentrate on is the methods of sealing off or capping off the cylinders, and to show the different methods and techniques involved. There's two main types of sealing WTCs using O-rings, and they are axial or radial sealing, and these two modules demonstrate that pretty well. The clear module we got here, that uses axial sealing, and that is where the actual O-ring compresses against the edge of the cylinder. So it doesn't actually go inside the cylinder, it just sits on the edge, and the face of the end cap, that compresses up against the edge of the cylinder. Now clearly for this type of sealing arrangement you need something that's going to actually provide pressure against the seal to make it work, and that is usually done in the form of either rods that are running either internally or externally to the cylinder that run 4.5. If you want to see a commercial example of that, just have a look at OTW or shear line modules, and you'll see an example of both of those types. The OTW modules run the rods internally and the shear line modules run externally, and there's advantages and disadvantages to both methods. The other method of of gaining compression of the seal is like the Robbie kits, the U47 and the Seawolf, where they actually use the equipment rack to pull the end cap and tension it up. And I think that's the best method because it gets one item doing two jobs, and you don't have all these control rods taking up room in the boat or inside the module itself, and so I rather like that method best. The second method of sealing the modules is known as the radial sealing method, and this is where we use a seal on the inside of the tube. And if I pull this cap off, you can see the O-ring it's inside a groove. This is a cast end cap. This is actually a commercial module sold by a company in Wales, and they cast the end caps, whereas these ones have been machined from sheet stock. I made these up myself, whereas these are a bought item. And the end cap has a groove cast into it, and if I take out the other end, I've taken the seal off of that, so you can see the groove more clearly there. The groove is cast in all the way around the diameter, and the O-ring sits inside that groove and sits slightly proud of it, and by doing that, when you push it inside the cylinder, that's a greater diameter than the inside of the pipe, the seal that's sitting proud there, and what that does, the pipe actually compresses the seal, squeezes it down. So with this type of sealing arrangement, you don't need any sort of pinching mechanism like rods or a tech rack to pull it to. It pushes itself to. So in some ways that's simpler and more elegant, but it is a little more difficult to make, especially if you don't have access to a lathe or something like that, because you do have to be very accurate with the diameter of that internal groove in order to ensure that you get the correct compression or pinch onto the O-ring seal. If you have two, if you machine the groove too deeply, then you'll end up with insufficient compression of the seal, and that will give you the potential for a leak. And if you have it too shallow, what tends to happen then is that the O-ring sits too high up, and you will find your end caps are either very stiff to push in and remove, or you might actually damage the O-ring seal trying to push them into place. So it's a little bit of a balancing act. And of the two types of end caps to fashion, these are definitely the harder end caps to make. And in fact, when it comes to making one, that is the one that I'm going to show you how to make, because if you can make one of these, an axial end cap is a piece of cake. Very, very easy indeed. And in fact, all the principles that we take into account with machining an end cap for radial compression can be used for axial. The only difference is that you don't have to bother about machining a groove in there. Okay. Just wanted to elaborate a little bit on the materials, because I've seen some questions come up on the forum about what sort of materials that you can use for making end caps. Most of the commercial units sold in the States seem to have cast end caps like this, where they're cast from a polyurethane resin, and I think a lot of people are under the misapprehension that that's the only way to do it. Clearly, for the kit makers, people that are doing it for a living, casting the end caps is an efficient and economical way of making the caps, because they're producing them in a degree of volume. But if you're just someone at home building up one or two modules, it doesn't really make any sense to go to all the trouble of making a master, taking a mould of that, buying the resin, casting the parts out, just for one or two modules. It's nuts. So it's much easier and far preferable, in my opinion, to actually get yourself some sheet plastic, which it can be polycarbonate like this is, it could be acrylic, it could be PVC, it could be ABS, almost any sheet plastic. It needs to be relatively stiff, and it needs to be relatively thick, at least twice the thickness of your cylinder walls. So in the case of this, 3mm thick cylinder walls, and I've got a 6mm end cap, and that would be considered about the minimum for this size of module. And just machine them out from that, and that's an easy way, and it's economical as well, because you can often get offcuts of plastic material very cheaply or free. If you know local sign makers or something like that, they throw out a lot of plastic sheet that is very suitable for making this sort of items, and you can save yourself a lot of money, which you can spend on other nice goodies for your submarine project. So as I said, I'm going to deal mainly with a radial sealed end cap, the construction of a radial sealed end cap, as that's the more difficult one to produce, and I think it's the one that most people want to know how to produce. The first job you need to think about before you do anything else is you need to decide what diameter cylinder you want to make, because that's going to dictate all the extra dimensions. And you also need to take into account the material you're going to use for the actual cylinder, because PVC and acrylic and polycarbonate, they all come in slightly different thicknesses. So the external diameter might be exactly the same, but the internal diameter will differ. So that will dictate as we're going for radial sealing method, that will dictate the kind of O-ring size that we're going to go for, and also the dimensions of the end cap itself. So in this case, in this example, I'm going to make end caps for this cylinder, And the reason I'm going to make end caps for this cylinder is that the company that produced these end caps made a mistake. They made them too small for the actual pipe. I don't know if you can hear that there. It's rattling, yeah, and that rattle, that indicates that they're very loose. Obviously there's not a seal there, and the one with a seal on doesn't rattle because the seal takes up the slack. But if you look down the actual barrel of the module, and I'm going to try and see if you can. Can you see it at about 12 o'clock down that module? Can you see right at the top there, there's like a sort of bit of a gap, bit of light poking through there, which shouldn't be there, and that indicates that there's actually a gap in between the seal and between the wall of the tube. And what that means for your model submarine is that it's going to leak like a sieve. So basically the mistake they've made here is that these caps are too small. The groove does not, that goes too deep, and you don't get sufficient compression of the seal on the inside of this pipe. Another thing that's worth pointing out with commercially produced extruded plastic pipe is that the tolerance of the pipe, or the spec for the tolerance of the pipe that it has to conform to, centres mainly on the external diameter. The internal diameter is far less important, and what they do, they pump water through under pressure through the pipe to cool it down when it's in the mould, when it's moulded, and by doing that you end up with a somewhat rough and bumpy finish inside the tube. It's far, and for the use that it has to go into, which is plumbing and guttering, this sort of pipe's used for, the fittings seal on the outside of the pipe, they don't seal internally. Right? But if we go for external fittings, that takes up more space, and that's going to make it more difficult to get the module inside the hull. So this highlights perhaps one of the slight disadvantages of using the radial method of sealing with cheap extruded plastic pipe, in that you haven't got an ideal surface to compress your seal against. An ideal surface would be a very high quality moulded surface like the outside of the pipe, and there are some pipes that you can get if you look around that have a better internal tolerance, but they're very, very much more expensive and they are more difficult to find. But having said that, the internal finish on here I think is adequate to get a good seal, providing we get a little bit more compression onto the seal, so that it squeezes up better around the pipe and takes up any inconsistencies in there. So I'm going to make up a pair of new end caps for this, and rather than make them from polyurethane resin, I'm going to turn them up from some sheet plastic, probably PVC like the tubing. I've got some of that in stock, and hopefully we should have a better dive module. Having decided that we're going to make up some new end caps, the next stage is to measure our pipe so that we know the sort of dimensions that we're dealing with. To measure the pipe, you've got a couple of choices. You can use some dividers if you have them. The best tool to use is a set of calipers. These are quite cheaply available now. You can purchase them online. You can get them at some sort of cheap discount stores. I typically pay around about £4 or £5 for a set of these, and they're great. Really useful tool for measuring all sorts of things on your model. Definitely something you should have in your toolbox if you can find a set. And what I'm going to do is use them 68.4, 68.27, 68.3. As you can see, it's not absolutely spot on because it's not a high precision product, but it's give or take about between 68 to 68.5 or so millimetres diameter, and in actual fact it's listed as 68 millimetre tubing. Having measured the external diameter, we then want to measure the internal diameter, and again I sort of measure it in several places so I get a good idea. 64.25, 64.3, 64.34, 64.3. I also know that this tubing is 1.8mm thick, so in theory I should be getting around about 64.4 millimetres internal diameter, and I'm getting roughly around about that figure. So it's pretty consistent. In fact, using my calipers, I'm getting actually about a 2mm thickness there. Yeah. 2mm, 2.2. So it does vary quite a bit. So going by that, there's our cylinder. So we know the outside diameter is 68 to 68.5, and internally we're looking at around about 64.2 to 64.4, and that's in millimetres. Of course, it's in metric again, so apologies to those of you who find it difficult to work in metric, but we are in 2013 now. So knowing those measurements, we can now go about calculating our O-ring size, because we know that what the internal bore of the cylinder is, and the external diameter of the cylinder is going to dictate our overall outside diameter of the end cap. So I will go to the upper end of that figure personally. So I will make my end cap 68.5mm diameter. And for the inside, I'll go to the lower figure for that. I'll go 64.2, because what I don't want is an interference fit in the cylinder. In actuality, what I will do when I machine this part up is I will make it to fit. So the best way of actually making your end caps is to have the tubing cut to size and trimmed, ready to accept the end caps, and then you make each end cap to fit, and that way you're guaranteed an excellent fit, and it takes account of any inconsistencies in the tubing, because like I said, it doesn't always follow perfect dimensions on the inside. So if you remember from part one, I said that for the majority of WTCs or modules that most of us want to make are between around about 2 to 4 inches, and some people might want to go a bit bigger, up to about 4 or 5 inches, or even 6-inch diameter for very large boats. In this case it's 68mm, and that's around about probably about 2.5 inches diameter, something like that. So we're right within the ballpark of what what we want to make generally. And I said that the thickness of O-ring that most of us would want to use is probably going to be around about 1/8 of an inch or 3mm in metric, and in this case I'm going to use a 3mm thick O-ring, and that is the cross-sectional thickness, if you remember, not the actual diameter of the O-ring, it's just the thickness measured across the O-ring itself. Now the next thing we need to consider is how much we want to actually push the O-ring down when we push our end cap home. How much compression do we want to squeeze it? And generally the advice given for what they call a dynamic seal, i.e. something that's going to move, is around about 10 to 15% of the O-ring thickness. So the O-ring cross section is 3mm, so we go 10 to 15% of 3mm. Right? So 10% is very easy to work out. That's just 0.3mm, and of course 15% would be 0.45mm. So that's around about, in imperial measurement, that would be somewhere within around about probably about 10 to 20 thou of an inch. So it's quite a small amount, and you can, if necessary, go up as high as 25% of the O-ring diameter. But if you go that high, you will find that your end caps are extremely difficult to push in and remove. You do run the possibility of damaging them as well if you're not very careful. So I would aim for 10 to 15%. And if you still find with 10 to 15% compression that you're not getting an adequate seal, you really ought to be looking for slightly better tubing, I would say, than what you're getting. You must be getting some very, very rough tubing. Either that, or you have the option of machining a collar, which could be then bonded into the tube with a nicely machined internal diameter. So that's an alternative. It's more work, of course, but that's one way of getting around that if you want to work with your existing tube. The second thing that we need to realise is that when the O-ring sits inside the groove of the end cap, we want it to go on with a little bit of snap, what we call snap. So basically, you shouldn't really use metal tools to remove rubber seals, but I've been quite careful there. Wooden or plastic tools are better because you don't run the risk of damaging the seal then. But anyway, basically, when your O-ring's fitted to your end cap, you want it to stretch a little bit so that when it goes onto the groove, it can't jump out the groove very easily. It doesn't flop about and move about. And there's a percentage of how much you want that O-ring to stretch to fit in the groove, and that percentage is given as between 1 to 5% of the O-ring diameter. So now we're not looking at 10 to 15% of the O-ring cross section, we're looking at 1 to 5% of the O-ring diameter. So going back to what we said before, that we need 0.3 to 0.45 compression on each side of the O-ring. We can actually work out the diameter that we want our groove to be, right? Because we know that our internal diameter, so that this is going to be the internal diameter around here of our, this put along here and along here, we know that that internal diameter is going to be around about 64.2. We also know that we're going to be using a 3mm thick O-ring, and we know that we want it to compress down 10 to 15%. So it's going to be, the depth of that groove is going to be 64.2 millimeters minus about 2.55 to 2.7 millimeters deep. That's how deep we want that groove to be in there. So, but at the same time, we also want some stretch on our O-ring. So, knowing all those parameters, we can now calculate our internal diameter of our O-ring, and the internal diameter for that I will now work out. Right, so the amount that I have calculated, or the inside diameter of the O-ring that I've calculated, is 58 millimeters. So how did I arrive at that? Well, I already know that the inside diameter of my tubing is around about 64.2 millimeters, right? And I know that my O-ring that I want to use is going to be 3 millimeters thick. I also know that I'm going to want about 10 to 15% compression of the seal, and I'm actually going to be working to the upper end of that because the tubing is not very well finished inside, so it's not hyper accurate, so I'm going to go for the upper end straight away. And I also know that I need about between 1 to 5% stretch or snap on my O-ring to ensure that it stays nicely in place when it's located into the groove of the end cap. So to get to 58 millimeters, I'm going to subtract from that figure 64.2. I need to subtract 2.55 twice from that figure, and that 2.55 is 3mm less the 0.45 millimeters on each side that I want to compress the seal down. So that's 2 times 2. And I also, so that gives me a figure of, what did I work that out to? 59.1. And also I want a little bit of snap. So any figure between 1 to 5% is acceptable. The optimum they consider is around about 2% of the O-ring's diameter. That's the internal diameter. So I considered that 58 millimeters, well, 1% of that figure would be about half, a bit over half a millimeter. So I just doubled it pretty much, and that gives me 58 millimeter. 58 millimeter is going to be an easy diameter O-ring to get. So it's not super critical, that part. You've got quite a bit of leeway there, but I know that 58 millimeter O-ring, and I could actually go down probably as far as 57. So it'd be 57 to 58 mil inside diameter, 3mm thick, and I'm going to be using nitrile. So we can now go ahead and order our O-rings, and having got those, we can then plan our dimensions for the actual end cap itself. So I'll get another little piece of card to draw on. Right. Now, for our end cap, we know that we want an outer diameter 68.5 millimeters, and we also want to turn a step down to 64.2 millimeters. So if we looked at it side on, yeah, we're going to have, and then we're going to have a step .2 millimeters. We also need to work out how deep we want that end cap to be. Don't know at the moment. Well, what we do know is the thickness of our O-ring. We know we've got to make a groove in this part for the O-ring to sit in, as like you've got on here. Now, with an O-ring, we talk about O-ring compression, but it's a bit misleading because we don't really compress an O-ring when we squeeze it. All we do is actually extrude it. We squeeze it into another shape. So the O-ring starts off a nice round shape like that, and as we squeeze it by pushing it into the tube, it ends up more of an ellipsoid shape, like that. That's exaggerated, but it kind of illustrates the shape it goes to. And as you can see there, that's a good bit wider than what it was in its original unsqueezed form, right? And so you need to take account of that when you're dimensioning the groove on your end cap. Now, some end caps I've seen, and these are included, they don't really do that. There's left a bit of a gap there, but it's not ideal because the actual groove itself, and this is another thing with these end caps, they've put a round groove in there, but the correct way to actually make the groove is square, so that the O-ring sits in there like that. There's plenty of air around it in the corners there, and it will sit very nicely on there. Now, the actual gap on there, the gap between this point and that point, right? The main thing is that it's got enough room for the O-ring to actually spread out into. So really, it's more of a minimum gap than a maximum gap. Obviously, you don't want to go too mad, but as long as you've got sufficient clearance, then you're all right. So we know that we're compressing our O-ring down 0.45 mil on each side, right? So that is the minimum figure that we want to add on to our overall diameter of the O-ring. So the O-ring is 3 millimeters, and we would want to add on a minimum of 0.45 millimeters to give us a figure of 3.45. And in actual fact, I would go more than that and consider something of around about 3.5, 3.6 millimeters. for the groove width machined into the end cap. Okay, I hope that's clear. I don't think that's too difficult to understand, and it's just to allow the O-ring to spread out. And either side of the slot we want a bit of material either side, just to support the O-ring. It doesn't have to be a huge amount, but what they've allowed here is about right. You've got around about 4 to 5 millimeters on this side, and around about 3 to 4 millimeters on the other side. So I would stay with that sort of figure, and then they've got quite a generous amount of allowance for the actual flange where it sits against the tube. You could actually afford to go quite a bit lower than that. 3 or 4 millimeters is quite sufficient, really. So based on that, I'm going to want around about a sheet thickness for this type of cap of around about 12 millimeters, and that 12 millimeters translating to imperial is around about ½ inch thick. So quite a generous an end cap, and that's one of the slight disadvantages, I suppose, of this method, in that you end up with a larger end cap than you do with the axial method of sealing. And what they usually do, especially if they cast them, they usually create a little pocket on the inside, so it thins out the disc a bit, which saves you a bit of weight, and it also gives you a bit of extra space inside the module, so the cap doesn't take up all that amount of room. Whether or not you want to actually go ahead and thin that out is entirely up to you as the builder. Obviously, if you choose a nice clear material like this to machine it out of, if you machine that pocket out, you will turn it opaque with the machining marks. But it wouldn't look that unsightly if it's done neatly. So basically, we can put a figure in there of about 12 millimeters for our material thickness. That's what I'm going to be looking for, and I think I've got some 12mm PVC stop in there, or something pretty close to it anyway. Right, here's some of the plastic that I've got. I've just measured it, and in actual fact it's about 14.5 millimeters, so more than what I need, but that's no big deal, because you can always take a little bit off, but you can't put it back on again. So plenty of material there to cover, well, probably about 4 or 5 discs there I could get out of that. But I only need the pair. So the next stage, you could make a better drawing of your disc than that if you wanted to. Usually for something simple like this, I just note a few of the dimensions down on a bit of paper, and that's sufficient for me to be able to machine them up. I find having super neat drawings is only really necessary if you're going to get the parts made for you by someone else, as obviously then they can't read your mind. So, but if you're going to be doing the machining yourself, just a few details is generally enough. So what you can do next is use the tube itself, because we're only going to rough these discs out. So just there. There we go, and what you can do then, if you follow the outside line, that gives you plenty of clearance there because we've got the thickness of the marker pen, and you can just cut round that, and you can cut these out either with a bandsaw if you've got power tools, jigsaw, or if you're really unlucky, you can cut them out by hand with something like a coping saw. But cutting through 14mm thick PVC by hand is not much fun. Okay, so I've got my blanks cut out now. So the next stage is going to be to you see that I've cut the corners off, but these sort of little edges here we can machine them off adequately on the lathe. So the next stage will be to mount them on the lathe. Now there's several ways of going about this. You can use a mandrel, but if you're going to use a mandrel, and a mandrel, for those who are not sure what that is, it basically consists of a post that you mount in the chuck, and it'll have a threaded shaft on it, and a couple of nuts, and you just hold that in the chuck. You drill a hole through the piece here, you bolt that into the mandrel, and then you put the mandrel into the chuck and hold it in the chuck, and it holds it outside of the chuck, and you can turn it up. The other side of the mandrel may sometimes be supported by the tailstop as well, but the disadvantage with using a mandrel is that you've got to drill a hole through the middle to hold it. Now in a lot of cases most people usually put a hole through the centre for the prop shaft to fit into, so in that instance it's not that much of a disadvantage to drill a hole through. In fact, it's to our benefit to do so. But for the cap at the front, you might not want a hole in the middle. So how would you go about producing a cap if, like this one, you wanted to keep it completely blank? How do you mount that? Well, there's various methods. An easy method is to turn up a blank on the lathe out of some wood or some other plastic, and like this, and on one side of there I've got glued on some abrasive. That's just a bit of glass paper that's been bonded onto the. This is a bit of PVC actually, a bit of PVC rod, and I've bonded on some glass paper onto there. This side would be held in the chuck and jaws, and that side will go onto the material, and by pressing on the other side with another piece of blank material, but without the friction part put on, it's just there to push the material against that. That creates friction. It works rather like a clutch plate on a car, and so that creates friction, and it holds the material in place. Obviously, if you're using this type of method, you don't want to be taking heavy cuts, because if you take heavy cuts, the chances are the tool will dig in and it will spin the piece off into the wire blue yonder. So you need to take light cuts with that method. Another technique is similar to this, and that is to, instead of using an abrasive, because an abrasive at the end of the day will damage any finish on the plastic, especially if it spins. So if a finish is important to you, what you can do is, instead of using abrasive, you can use double-sided tape, the sort of stuff that they use for sticking carpets down with. That's a thin double-sided tape, and you put a layer of that on, and it's very fat, usually about 2 or 3 inches thick. You put a layer of that over, and then peel off the backing, and you stick your work onto there. Now obviously when you finished your work, you've got to get all your machining operations done in one hit, because once you finish your work you'll have to destroy that bond between the work to get it off. Yeah. Usually what I use, I just put a bit of turpentine or something like that in between, and that's, or WD-40 sometimes works as well, just to loosen the bond enough to peel it away. Something else you can do if you want to carry on using this abrasive method is to just stick something like electrician's tape, or even sort of something like sellotape across the surface of the plastic, to protect it against the abrasive. Or you could even stick, I don't know, a bit of scrap cardboard, bond that on. So there's all sorts of things you can do. Use your imagination. But like I said, you can if you drill a hole through, you can just use a mandrel, and a good makeshift mandrel can be made out of just a long bolt with some nuts to run up on it. It's makeshift. It's not particularly high precision, but this isn't particularly high precision engineering. It's fairly basic engineering, and we can get by with quite crude methods. So what I'm going to use for this, I'm going to make one using a mandrel, and I'm going to make the other one using the old friction disc here, just to illustrate the differences. Okay, so I've got one of the discs set up in the lathe. I've got quite a large lathe to use here, but you don't need a big machine to be able to do this sort of work. Working with plastics is pretty undemanding on lathes, even small ones. The only thing, if you're working with a smaller machine, make sure you take light cuts, don't take heavy cuts, because it will just drag the machine down. But holding work in this way, and working on this sort of material, you can't take heavy cuts anyway, because it will just fling out of the out of the chuck. It's only being held in place with a bit of friction here. So plus, if you start taking very heavy cuts on plastic, what tends to happen is it just all melts around the tool. All I'm using here is just a standard side and face cutter to just basically just take this disc down, so that we've got a nice uniform diameter. As you can see, I've already taken a bit off the disc, and it turns up very, very easily indeed. I'm running at a fairly moderate speed, about 300 RPM, and yeah, I'll just show you a bit of what I'm doing. As you can see, the machine's very, very easily, it's like butter. Just taking light cuts and not going too heavy. There's no rush. It won't take very long to get this machine down to the right diameter. It's taking off around about 32nd of an inch, I suppose, at the time. Although, as I say, it's a metric lathe, so all the dials are calibrated in metric, even though it's an old English lathe. So sometimes the swarf coming off gets tangled around, but as you can see there, we're down to a nice round disc now. Finishes off lovely as well, this material, very smooth, no machine marks at all, beautiful. Remember, this is just what I've done. I've backed up the disc that I had with some electrical tape, like I said, to protect the surface so we don't get that scuffed up, and that is just being held with the pressure from the tailstock pushing up against this disc from this side, pushing against this part here which is mounted in the chuck. And I'm using on the other side, I'm using what they call a rotating centre. So that's a ball race centre, but you could use a dead centre in there with some grease around there, but it's better to use a rotating centre if you can. Okay, so I'm getting quite close to where I want to be now. So I'm just going to get my calipers and I'm going to measure it. So 72.8. So yeah, it's not quite a way to go yet actually. So, as you can see, the swarth wrapping around is a little bit of a problem, so you need to just stop and take a heavy cut like that and just pull it off. It's a bit like silly string. If you're machining acrylic, I find you don't tend to get these sort of strands wrapping around so much. It tends to come off a bit more cleanly. It just varies depending on the plastic. I find the sort of softer and chewier the plastic is, the more likelihood you have of this swarf wrapping around the work the way it does. Whatever you do, don't be tempted to try and remove it whilst the machine's running. That's how people lose their fingers. Okay. .25, so I need to take about another 1.5 millimeters off. So let's do it. And that's our blank machine down. We've probably got we could take just a whisker off if we wanted to there. Because on the readout, because I want about 68.5 and I've got about 68.9. So I'm about 0.4 mil over. That leaves me a little bit just to clean up if I want to at the end, so I'm going to leave that until I've finished off machining the step that I need to machine in, and also the groove that I'm going to machine in there as well. So I want to now take this down to the next level, which is the inside diameter of the tube. So I want to step that down. So that dimension is 64.2 millimeters, and I know I'm at 68.9 thereabouts at the moment. So I'm going to go down in 1 millimeter increments, which is going to take 2 millimeters off the overall diameter. Again, getting the build up the swarf. Usually like to remove that before it gets to a point where it's going to really affect the machining. My ability to see what I'm actually doing. And this gives me an opportunity to measure how far in. Now, as I said before, this is not precision engineering, so I'm just using really sort of jobbing tolerances for this. This, I think. I've gone in there around about 11 millimeters, so it's a bit under half an inch into there, and that's where my step's going to be. So for subsequent turning, I will go up to that shoulder there. So taking off about, should be getting close to about 4mm off the overall diameter. I'm down to 65.34 now. So I want to take off about another millimetre or so. Using the dials here just to see how much I'm taking off. Obviously this stage you need to take a little bit more care because it's very easy to take too much off at this point. 64.4. Right, and there we go, we've got our shoulder nicely machined, and we're machined pretty much down to the diameter we require. 64.41, probably do with just taking a tiny amount more off so that we don't have too much of a tight fit. .3, so cylinder again. What we could do is taking just a little bit more off there. And there we are, 64.2, 64.23. That's close enough for me. So having machined our shoulder down, the next thing to machine is the channel or groove for the O-ring, and for that the tool that we use, or the tool that I just use a normal parting off tool, which is a small square tool. This one is around about, I think it's around about a 1/16 inch thick. Yep, about a 1/16 or couple of mil or so wide. It's not that critical because you can move it along to widen the groove, and as I said before, it's the depth of the groove that's rather more important than the actual width. The main thing with the width of the groove is to ensure that you've got sufficient clearance for the O-ring to expand as it's compressed, so, or squeezed down I should say. So we want our groove to be set around about 3.5 to 3.6 millimeters wide, and I've got, my channel is about 10 mil deep. So I want to go about 3 mil. And set back where I want to put my channel. I'm going to start in around about 3 millimeters, or about 1/8 of an inch in from the end of the end cap. Again, the position doesn't really matter, it's just you want a bit of shoulder each side of the O-ring, just for strength really. Again, I'm going to spot on to my work to get my reference. That's it. Zero my dial. Now I know I'm at 64.2 and I need to go in, what's the measurement that I had? The measurement that I had for the depth of the groove is 2.55. Okay, so that's the depth that I need. Right. 1 mil. Two mil. Two 2.5. 2.55. So that's our maximum depth now. I'm now going to wind out there. Stop, clear my swoof off. Now what I've done, I've zeroed my cross slide here, and I'm going to wind along the length that I want. And bear in mind that I've also got to take into account the tool width, and that is, I'm going to measure that precisely. One and a half mil. So the width of my groove wants to be about 3.5 to 3.6. So that means I want to roll along about 2 millimeters. 1, 2. And I'll go back again. Double check with the rule, make sure that I've got the right clearance there. That looks pretty much spot on, lovely. Right. Once again, I'll plunge in 1, 2, 2.5, 2.55. Loads of swarf here. I'm just going to pull that off. And there's a little bit in the middle. I'm going to wind back about halfway. And just going to plunge in 1, 2, 2.5, 2.55. There we go. If I zoom in there, there you can see we now have an O-ring. This is the shoulder that will, the shoulder here that will butt up against the edge of the tube, and then we have the inner diameter plus our groove for our O-ring that will sit in there. If we want to go a little bit further, we can put a little bit of a chamfer on the edge here to finish that off nicely, and we could also put a little bit of a chamfer on each edge here so that you haven't got any sharp edges that can cut into the O-ring. That's entirely optional, but you could add them in. You could even add them in with a little bit of sandpaper afterwards if you wanted to, but far from essential. So that completes endcap 1, and the next one is going to be made on a mandrel to show you the turning process for that, which is identical to this, except the only difference really is the way it's actually mounted. So the actual turning process is exactly the same, it's just that we mount it on a spigot instead of using friction like this. Okay.